Hello and welcome, everyone. Today we're going to dive into one of the universe's biggest secrets, gravitation. It's this incredible, invisible force that literally holds everything together, from the biggest galaxies all the way down to you sitting right there. Seriously, without it, our planet would just fly off into space and we'd all be floating around. So, let's figure out how it all works. Have you ever just looked up at the moon and wondered, why is it just hanging up there? How does it not just fall down? Or an even simpler question, what's stopping you from floating right out of your chair? The answer to both, of course, is gravity. It's the one force that connects everything, from a tiny cricket ball to a massive star.
So here's our plan for this explainer. First, we'll talk about this invisible pull all around us. Then we're going to decode Newton's secret formula, and don't worry, I'll make it really simple. After that, we'll tackle the question of why we aren't all stuck together. Then we'll zoom out to see how gravity runs the show on a cosmic scale, and finally, we'll bring it all back home to understand what keeps us grounded.
Okay, let's get right into it. Time to start with the most basic idea of all. What exactly is this force? Well, get ready for this, because it is as simple as it is mind-blowing. The universal law of gravitation says that every single object with mass pulls on every other object with mass. I'm not joking. That means right now, you are pulling on the screen you're watching this on, and the screen is pulling right back at you. Your chair, your book, the planets, even stars light years away. Everything is in a constant cosmic tug-of-war.
Now, the great Sir Isaac Newton, he didn't just stop there. He actually gave us a secret formula to calculate this force. I know, it might look a bit scary, but trust me, we're going to break it down into really simple parts.
The first ingredient in this formula is mass, and this one is very straightforward. The more stuff an object is made of, the more mass it has, the stronger its gravitational pull. Think about it. The Earth has a massive gravitational pull because it is, well, massive. A small stone also has mass, but its pull is tiny in comparison. So more mass means more force. Simple, nah? Our second ingredient is distance. And this is where things get really interesting. Gravity gets weaker as things get farther apart. But here's the catch. It doesn't just fade away gently. No, it drops off super fast. This is what scientists mean when they say the force is inversely proportional to the square of the distance. So, when we combine the mass and the distance, we get Newton's complete, brilliant formula. The force, F, equals the two masses multiplied together and then divided by the square of the distance. But wait, there's one more piece to the puzzle. All of that is multiplied by a special number g. This is the universal gravitational constant. And this g, it's the key to the whole thing. Okay, time for a quick challenge. Let's put that inverse square rule to the test. Here's a question for you. If we double the distance between two objects, what happens to the force of gravity between them? Does it get half as strong or something else? Have a think about it for a moment. Got your answer? Let's check it with a really simple trick. I call it invert and square. So we doubled the distance, which means we start with a number 2. Step 1, invert it. So 2 becomes 1 by 2, or a half. Step 2, square it. So 1/2 times 1/2 gives you 1/4. And there you have it. When you double the distance, the force becomes 4 times weaker. Not half, but a quarter of what it was. This is a super powerful rule. It's exactly why we don't feel the gravitational pull of distant stars. Even though they are unbelievably massive, they're just way too far away. Okay, but this raises a very practical question. If every single thing is pulling on every single other thing, why aren't you being pulled towards your desk right now? Why aren't we all just clumped together? Well, the answer lies in that mysterious g we talked about. The whole secret is in the value of g. Just look at this number.
See that minus 11 up there? That means this number is incredibly, incredibly small. I mean, to write it out, you'd put a decimal point, then 10 zeros, and then the 6. It's almost nothing. And this unbelievably tiny number, it changes everything.
So here's the main point. Because g is so tiny, you have to multiply it by some truly enormous masses for the final force to be anything but weak. The gravitational pull between you and your phone definitely exists, but it is so ridiculously small that you'll never ever feel it. You need something with the gigantic mass of a planet or a star for gravity to finally show its real strength.
All right, so let's zoom out. Let's leave our everyday objects behind and go to the cosmic scale. Let's see how this unbelievably weak force becomes the master architect of the entire universe, controlling everything from our moon to all the planets. A great way to picture this is to imagine swinging a stone tied to a string. The string is constantly pulling the stone inwards, right? That's what forces it to move in a circle. That inward pull is called a centripetal force. Well, in space, the Earth's gravity acts like a giant, invisible string connected to the moon. It's always providing that centripetal force that keeps the moon locked in its orbit. If that invisible string were to snap, the moon would just fly off in a straight line, deep into space. And it's just incredible how many things this one simple law can explain. It's why the moon orbits the Earth. It's why all the planets, including our own, orbit the sun. It even explains why the tides in the sea rise and fall every day. And, most importantly for all of us, it's the force that binds us to the Earth. So let's bring it all back home. How does this giant cosmic force create that simple feeling of being planted on the ground? To really understand this, we need to be very clear about the difference between two words we often use as if they're the same: mass and weight. Okay, let's break this down. Your mass is basically the amount of stuff you are made of. It's measured in kilograms, and this number stays the same no matter where you go in the universe. Your weight, on the other hand, is the force of gravity pulling on your mass. And since gravity can be different in different places, your weight can change. For example, on the moon, you'd have the exact same mass, but since the moon's gravity is much weaker, you'd only weigh about 1/6 of what you do on Earth. So, that feeling you have right now, that force pressing you down into your chair, that is your weight. That is you, personally, feeling the Earth's huge gravitational pull on your mass. It's the force that keeps you and everything around you totally grounded. This whole idea is captured so perfectly in a quote that's often linked to Newton. The true genius of his discovery was that he realized it wasn't two different sets of rules, one for things on Earth and another for things in space. No, it was one single universal law that explained both the fall of an apple and the orbit of the moon. For its time, this was a completely revolutionary idea. Now, when an object, like that apple, is just falling toward Earth and gravity is pretty much the only thing pulling on it, we have a special name for that. We call it free fall. And things in free fall don't just drop. They get faster and faster. Yeah, objects in free fall speed up at a very specific rate, which we call g. Here on Earth, g is about 9.8 meters per second squared. What that really means is that for every single second something falls, its speed increases by another 9.8 meters per second. That's why falling from a higher spot is so much more dangerous. You have more time to pick up speed. And this leads us to a super important point that trips a lot of people up: the difference between mass and weight. Your mass is just how much stuff you're made of. It's the same everywhere. But your weight, that's the force of gravity pulling on your mass. And since gravity is different on different planets, your weight can change dramatically depending on where you are. Let's take the moon, for instance. It's way less massive than Earth, so its gravity is much weaker.
The result is that you would only weigh about 1/6 of what you weigh here. Your mass, the amount of you, is exactly the same, but the force pulling you down is completely different.
So if gravity is always pulling things down, how on earth does a giant cruise ship float? Well, it turns out gravity's effect on water is actually what creates the upward force that makes it possible. It's kind of cool.
Okay, so when you put something in a fluid, like water, that fluid pushes back up on it. We call that push the buoyant force. It's why you feel lighter when you're in a pool. It's always fighting back against the downward pull of gravity. So you can picture it like a tug-of-war. You've got gravity pulling down with the object's weight and the water pushing up with the buoyant force. If weight is stronger, the object sinks. If the buoyant force is stronger, it floats. It's just a matter of which force wins the battle.
But how strong is that upward push? A brilliant Greek scientist named Archimedes figured this out ages ago. The buoyant force pushing up is exactly equal to the weight of the water that the object pushes out of the way. And that's the secret to a giant steel ship. Its shape displaces a massive amount of water, and the weight of all that water creates a huge upward force, bigger than the weight of the ship itself.
We've seen the formula, we've seen its effects, we've even seen how it makes things float. Now, let's zoom all the way out and just appreciate what an incredible job this force does in shaping, well, everything.
I mean, really think about it for a second. Without gravity, there's no doubt. We'd float right off the Earth. The moon would be gone, the planets would fly off into deep space. Even the daily rhythm of our ocean tides is caused by gravity's pull. It is, without a doubt, the master architect of our solar system.
And that leaves us with one last kind of mind-bending idea. Of the four fundamental forces of nature, gravity is by far the weakest. A tiny fridge magnet can overpower the gravitational pull of the entire planet Earth. And yet, gravity is the one in charge of the cosmic dance of galaxies. So why is it that the weakest force is also the one running the entire show?